Hi everyone. Hope everybody's doing all right. Today we're going to talk a little bit about probability and probability theory and some of the things that underlie that for this segment of the course module at least and bring into why all this stuff's relevant hopefully. So far we've been talking a lot about descriptive statistics and the things you've been doing largely have been based on descriptive statistics, describing essentially what data means, right? Getting the percentages, the frequencies, and cumulative frequency, cumulative percentages, and those types of things. But that's what descriptives are, and we covered this in chapter 1. What a descriptive statistic is, it describes a distribution of a sample or a population, right? It's helpful for letting you know what data is, what it looks like, and being able to inform people about what the data set you have is telling them, right? And one of the things is really limited in that capacity, and it's just essentially describing what you have on hand. Now, when you're trying to develop knowledge or test theory or move forward and advance knowledge within a field, not just criminal justice, but within all fields, right? They like to incorporate the idea of inferential statistics. And inferential statistics are statistical tools for estimating how likely it is that a statistical result is based on data from a random sample, right? So there's a lot that underlies that, the ideas of random sampling and determining whether that sample in and of itself is representative of the population. So that's essentially what you're trying to do in inferential statistics. Taking your information, saying if you want to see, people's delinquency habits or whatever, and it's kind of difficult to do that. So in the aggregate, in a large scale. So if I wanted to look at all the delinquency rates in the state of Texas for kids and youth and who are smoking marijuana or whatnot under the age of 18, trying to access that is difficult. So we try and generate a random sample where everybody has a chance of being included. And that's what I mean by random, right? That everybody has a probability, a known probability, a non-zero chance of being included. And through that, if you're able to do that through an unbiased estimator and achieve the sample, the results you obtain should be able to be generalized back to that population. And that's what inferential statistics are basically attempting to get at. So what underlies it all is probabilities, or the theory of probability itself. Now, probability theory, it gets really complex. It can be very difficult to understand. We can spend a whole semester teaching a course on probability theory itself, and there are places that do. But it's got a lot of complexities, and I'm just going to use this video kind of break it down to get to the meat of it all, and the big points that we need for us going forward within this class at least. But because probability is its own branch of mathematics, and but we use it every day, and that's what I was trying to convey here is examples that you think, what are the chances of winning in lottery? What's the chances of getting struck by lightning? What's the chances of getting pulled over if I run the stop sign? Or you know, if somebody's drinking too much at a bar or something, what's the chances of them getting pulled over on the way home or getting into an accident? Those are all relevant things. Or what's the chances of your plane crashing versus getting in a vehicle accident, a motor vehicle accident? Those are questions that are asked and they're consistent with probabilities, right? So it's defined, a definition of probability itself is defined mathematically as the number of times an event can occur relative to the total number of times that an event can occur, okay? So it's just the number of times in the numerator divided by the total number of possible times that that event can occur. So it measures how likely a particular event is to occur relative to the number of times that any event can occur, okay? Or how likely an outcome is to result, right? A particular outcome at least, right? So here's kind of a quick example, two quick examples. So um, on its face, it should be kind of easy to get understand. Um, so how we annotate it really oftentimes is with an A. So the probability of an event is, and this is how it's often annotated. So the total number of times that any event is often referred to as the number of trials. So say we want to understand the chances of pulling an ace out of a deck of cards, and there's 52 cards in the deck, right? So this would be the formula: the probability of um, getting an ace, pulling an ace out of a deck of 52 cards. So before there's 4 aces, so that's the total number of events that can occur. I mean, chances that you have, and this is the total number of events that can actually occur. So you just divide that, and you have about a little over 7.5 chance of getting an ace from any card, right, that you pull out of a deck of 52. Determine that you're not using a biased mechanism to pull the cards, and the deck has been shuffled, and all those types of things, contextual things. Flipping a coin, probability of getting the heads. So this was be the simple equation. The probability of heads. There's one heads and two possible outcomes, right? There's either heads or tails. That's the complete outcome. So you have a 0.5 probability or 50-50 chance of achieving a heads when you flip a coin through an unbiased process, right? Now, there's 2 points to remember: the number of times an event can occur in a given number of trials. So in one flip of that coin, it means that you have a 0.5 probability of achieving a heads, right? It doesn't mean that every time you flip a coin 10 times, you're going to get 5 heads and 5 tails, okay? That's more theoretical, and that's how things should work out. But the reality in real life, obviously, it doesn't work that way. I can flip a coin, and it's probably going to end on heads 3 times and tails 7 times. And all those types of things. But each event in this type of example is independent of one another, okay? And I'm not going to get too much into independence with it as of right now, but your text actually goes into a lengthy discussion that might be confusing to some degree. Y'all don't necessarily need to know the full extent of that. Getting into mutually exclusive and those types of that discussion as well. But tells us what is likely to occur in the long run. All right, this is the second point. So if you repeatedly flip a coin 10 times, say if you do it 10,000 times or 100,000 or 1,000,000 times, it will most likely be 5 and 5 on average, because that's just over time. That's a law of large numbers, and we're going to get there in a minute with this, hopefully. So there's a couple of approaches to probability. There's the theoretical, there's the classical approach, and it's interesting event A happening. Okay, so the probability of an action over the total number of possible outcomes. How probable something is likely to occur. Basically, that was what I was talking to on the front end, right? If you flip a quarter, if you flip it 10 times, it should be, in theory, 5 times on heads and 5 times on tails. So one thing I want y'all to know, it's a big point. Probabilities only range from 0 to 1, right? 0 to 1.0. And you can see that through the math, okay? If there's a total number of possible outcomes by the event that you're looking at, that should just make sense. It's simple division in itself, okay? The numerator should always be smaller than the denominator, or equal to or smaller, less than, okay? So if I flip a coin, it's either heads. It's either a 1 or it's a 0, okay? And that's the range right there. I can't have a 10 through one flip, and I can't have a -5 or whatever. It's just either heads or it's not heads. So if I'm rolling a dice, and I want to get a 1 and see my probability of getting a 1, I have a 1 in 6 chance, right? 1 over 6, that's the probability, or it's 1.166, or about 16.6, chance of getting a 1 on any throw of the dice, right? So if you want to get a 4, say if I want to get 2 numbers, okay, 4 or a 6, so that's 2 over 6, or 1/3, right, or 0.33 or 33.333%, okay, chance of doing it. So it's either 0.166 or 0.33, or if I want to have all 6 numbers, it's either 6 over 6, it equals 1. So it's within that domain, it's within that range, all right, from a 0 to 1, and that's where probabilities are going to exist. It's important to know that for future reference as well. Now, that's kind of the theoretical approach, right? The empirical approach, this is reality, like looking at things in reality. Empirical is looking at evidence that you can use to support that. Uses actual observations, and that's what empirical really gets at, right? It differs from theoretical because it's the probability equals the number of times that A actually occurred over the total number of occurrences. Okay, so we're looking at the actual occurrence itself. So if I flip a coin 10 times, I observe head 7 times, then it'd be a 7 and 10, right? Or 0.7 probability, because that's a quick, if you do that really quick, that division real quick, you can get a, a closer look into the number in the theoretical approach by increasing. So if I want to get towards the theory, I can increase it, and this is the law of large numbers. This is what I get. This gets you closer to that. It should be 5 times. It should be heads 5 times. It should be tails 5 times, or it should be the probability of 0.5. If I do it 20 times, or if I do it 100 times, or if I do it 1,000 times, the law of large numbers states that over time, if I'm using an unbiased mechanism to flip that coin, that over time eventually everything is going to start working itself out. These nuances that occur, these anomalies that occur, that it's going to be 7 times, it's going to be 0.7 to whatever. It should eventually get closer, a lot closer. It's not necessarily going to be 5 to 1,000, but if I did it 10,000 times, it's not going to, the chances of it being 8,000 over 10,000 is much less than, 5,100 to 10,000. Hopefully that makes sense. So law of large numbers is that it gets closer to the true theoretical as you continue to administer trials. So as you continue to grow that number, as I continue to increase my sample size, on looking at, instead of looking at just 10 kids in school or 100 kids in high school, how much weed they smoke, or 1,000 kids, or 10,000 kids in high school. I'm going to get closer to that true number, the actual number that exists within the population. So this normal curve, it's always going to follow us, right? So it's like a probability distribution as well, and all this stuff relies on it. And we talked about measures of central tendency and standard deviation and its variance, and calculating using the mean here, right? And I kind of alluded to it before talking about z-scores, but in standard deviations. And this is what a normal curve with standard deviations would look like. So 0 to 1 to 2 to 3, right? So in a probability distribution, all of the possible outcomes of a trial and the associated probability of each outcome are observed. So, demonstrated. So it's not something that's necessarily observed. It's based on theory itself, okay? But it has 2 pieces of information. It has every possible outcome and every possible outcome's chance of occurring, okay? So if we have 2 dice, just to break this down, so we have 2 dice, and we're going to look at all the possible outcomes. I could have a 2, I'm going to roll them, okay? I could have a 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, 11, 12, right? Because that's 2 dice. So I can either have snake eyes 1, 1, all the way up to a 6, 6, which each equals 12. But it also shows every possible outcome, right? And every possible outcome's chance of occurring. And that's what these probabilities here are. So I got a 1 in 6 chance of hitting a 7, right? And if you look at it, it formulates this normal curve, okay? Just like that. And that's just based on how things work. Now, if we're going to flip a coin and we want to look at flip a coin twice, we want to see if it was heads heads, it'd be heads tails, tails heads, and then tails tails, right? So the heads heads would be a 0.25, and the tails tails would be a 0.25 probability. But the heads tails and the tails heads collectively, so that's 1 and 1, equal 0.5. And if you add all that up, it equals 1. Alright? So hopefully, I don't want to get y'all too confused, but hopefully you get grasp a little bit of that, okay? And kind of see how that works out, right? So in inferential statistics, when you're making assessments and making assertions with sample data, it's going to be probabilistic. So the idea of inferential statistics is taking that sample of 100 kids from the state of Texas high schools and trying to see how much weed they're smoking, right, within a given year. And it's trying to take that 100 kids and make assertions about, the million kids who were in high school and their weed smoking habits, because it's too costly, too time consuming, too difficult to access 100, a million kids that are in high school and their weed habits. But it might be a lot more um, practical to get 100 or maybe 500 or 1,000 even, right? And perhaps from different schools where everybody had a chance to be collected. So the idea is to have that and get those sample statistics, and the conclusions will be probabilistic. And then you want to use those. And inferential statistics is the process of using sample data to make statements about the population itself. So I can take that 1,000 kids from that sample. If I achieve that sample in a non-biased, random fashion, and by random I mean, everybody had a chance of being included within that sample, um, then I can make inferences towards the population and kind of make assessments. It's what the NCVS does, right? I ask everybody this all the time. How many of y'all have ever taken the NCVS, the National Crime Victimization Survey, right? It's a big survey. It's on the full extent of victimization that occurs within the U.S. How we do that? Well, I've never taken it, and I'm just going to assume that you haven't either. But they assess households, and everybody in the country theoretically has a probability, a chance of being selected and included in that, and ask the extent of victimization. But for whatever reason, you're not. But anyways, they use that. They use that data to make inferences towards, the residents in the United States and toward the full extent of victimization. Now, extending the theoretical portion of that from probability, what underlies probability distributions is sampling distributions and the theory inherent in that. So a probability distribution of a sample statistic drawn from a large sample population. So when you're taking a sample, you're sampling from a population, okay? And this let's put this in, hopefully you can see this picture well. See, this is the population, the average, the mean, okay, of the population, the mean of high school students and their weed smoking habits in the state of Texas, okay? So say if we sample from, 100 kids or 1,000 kids from, the state of Texas, and then we get a mean here, okay, our average here. And then we take another sample of 1,000 kids, and then we get a mean here, then we get a mean here, and then we get a mean here. All right, we keep doing that process over and over and over and over through an unbiased procedure. Eventually, all this is going to build up, and we're going to get essentially the mean of the population. All right, now a sample value comes from an infinite number of potential samples from the population. A sample of 500 people is different when taken at different times. This is the concept of a sampling distribution. So if we sample from a population, from a given population, if we sample 1,000 kids from a million in high school, and then it's going to be different at different times in different places. But if we keep doing it over and over and over and over and over again in an infinite way, eventually it's going to be here, because eventually we're going to have everybody included within it if we keep sampling and sampling and sampling and sampling. All right. Now, the last point within it, I know it might seem a little confusing, a little tricky. Um, I just want y'all to understand the basics of it, the basic honest face of it, and the definition of it, and trying to understand that this exists. Okay, that's what a sampling distribution really is. It's saying it's acknowledging the fact that the sample that you achieve comes from, you know, the population itself to some degree, and then that it can potentially be different from the mean. But if we continue to do it over and over and over and again, we'll get towards the population's mean. So, the last piece I want to talk about is the idea that larger samples are better, all right? Because if you have 1,000,000 people in a population and you're trying to get towards that, a sample of 100 people is going to be prone to more error. You might have, you know, by some chance, you might just have 100 kids that are all in, you know, in a private school, you know, in private schools, and they come from, you know, backgrounds where, you know, nobody does smokes marijuana whatsoever. Or you might get a different group of kids here who go to schools that are just, you know, full of marijuana use and drug users and those types of things. So it can stretch all that. But ideally, if you turn that 100 into 1,000 to 10,000, you're getting closer towards this 1,000,000. All right, and the variation from the mean is less and less likely each time that occurs. Okay, the variation from the true mean, from the true mean of the population. And that's what the central limit theory gets at, right? A sampling distribution of any statistic will approximate normally as the sample size increases. So as the sample gets larger, you're getting closer to the population, and that's reducing the error. That's reducing the error in the size of the sample itself, okay? I'm going to ask y'all to watch another video as well to hopefully explain this one a little bit better, but you know, hopefully I got some of the good points. I think the larger points about probabilities themselves, it is kind of confusing, it is kind of tricky, and just want y'all to understand the little basic fundamentals that we discussed today, okay? Um, I hope y'all are good. If y'all got any questions, feel free to let me know, okay? Let's see ya.